on, and hopefully you've also been creating your own printed circuit board designs, because it is a really helpful tool if you are able to create your own circuits. So, no, without any further ado, so this is the circuit board that that we have created. Let's just call it that. Now I will be comparing it to our design and also what we actually physically got back. And I'm also using my secondary camera. So just if things go wrong, just let me know. And let's have a look. So I'm going to be sharing my screen and we'll just remind ourselves of what it looked like. What our design looked like and what we actually got. Before I do that, let's just talk about the board. So the board that I did get back, it's exactly the correct size. I think 71 by 69 millimeters, as we have in our design. I feel it is really well made. It is really stiff, and it doesn't feel like it's going to break. It is relatively thick. 1.55, 1.6 millimeters, which is, it doesn't sound thick, but it's really stiff and thick, and it doesn't feel like it's break. I did test the board. So usually the manufacturers will test your board, and then you will see if that works, or if that's you test the connections. So you can take a multimeter, test them with the continuity tester, see if it does make connection. It does have the nice green resin and also the silk screen on top. There is no silk screen at the bottom because we don't have any components at the bottom side. We only have components on the top side. And yeah, I'm actually really impressed with this board. Okay, so I'm going to be sharing my screen. And this is what the design looked like. Yes, so this is what the design looked like. We have our power delivery through connectors, but it's not really going to be connectors. It's going to be those 9-volt battery wires coming in to a regulator, which steps down the voltage from 9 volt to 5 volt. Now, this is probably something I did not speak about. Usually, if you have a power delivery circuit like this, you will have other components attached to this regulator. If you have a more complex circuit, that is something you might do. You might have filter capacitors in there to filter out the outcoming signal, and a couple of other elements in there as well to help to give you out a smoother signal. But for this project, I opted not to do that, just because I don't think we necessarily need this for this specific project. But if you are creating a project, it might be a bigger project. Just remember that you might have to add in a couple of components in the power delivery side just to smooth everything out. So going back to our schematic, this is our schematic representation where we have our connector, our IC flowing into the our switches with our pull down resistors going into our first IC of exclusive OR gates, then our second IC with AND gates, and then running into our third IC of OR gates, into our current limiting resistor in series with our LEDs. Now on the board, it looks like this, where we moved around our components. but our power delivery is still up there. We have our switches, our IC1, IC2, IC3, with our pull down resistors here and also one over there. Exclusive OR gate, our AND gate and our OR gate, heading into our current limiting resistors, finally feeding into our LEDs. And our manufacturing looks like this. This bigger. Yeah. So the next thing you should see is the so like the component viewer. Now this isn't like ideal, but this is what the board actually looks like. So this is our first board. I can't zoom it out enough because else we'll lose a little bit of detail. But this is roughly what it looks like. It looks exactly like the design that we sent them. The silk screen and everything is perfectly representative of what we wanted to do. Up here, remember we have our, this is embedded inside the copper as well with the, this is our first board, our first board. Sorry, let me just close this, is this embedded copper, and then this is on our names layer. And this is now as well, you can see this is inside the copper. And then this is the on the names layer. So everything you have on the names layer, you will have on the silk screen. And as we spoke about as well, I made a little mistake where the writing of my incoming power and my IC4, the regulator, are on top of each other. Now, remember I spoke about I needed to move that, but I didn't. And it's also reflected in our manufacturing design document. And I should really have seen it over here. But I mean, it doesn't really matter. It doesn't impact the design or the functioning of the circuit, which is the important thing. But what it does do is it does not look very nice. So this is another example of you have to check and recheck your design, because everything on the names layer, they will print out and it doesn't really matter what it looks like. They will print it out as is, because it doesn't, they cannot tell if it's if you've done that on purpose or it's a mistake. So this is our top layer. This is our bottom layer. And as you can see, our bottom layer does not have a silk screen. We only have our lines and components. Now, if we have this view here, bottom left or top left next to our grids, we can click on layer settings, and then we can deactivate a couple of layers. So let's deactivate our bottom layer so it disappears and we don't want to see that. So we can only focus on our top layer. So click OK. And now we can have a look at our design. If it follows the same pattern. And it pretty much does. You might be wondering, well, okay, but where is this element running here? Well, that is ground. Now, when we click on the rat's nest, remember this happens. So we filled in our filled copper. So this ground connection is not connected because it is connected via ground. And that is exactly what happened with this connection. Now this line disappears because it is within the copper fill. So underneath this resin, there is copper. And our first connection lines, we only really see from our connection from our switches, a connection line running there and running through there, which is exactly what we see. And we can also see that this keep out, well, this element where all the copper is removed is also there where all the copper is removed. So we can clearly see that all of the circuit designs move exactly like we expected it to. Now, another thing that is that the manufacturers added, which we did not, is this little number on the bottom left. Now, on our manufacturing element, we do not have any a element there. And you might also see that there is a, over here on the sides, we have this zone, which we can also see over here is the zone where there's no copper. That's to do with our design rules, where we have a minimum distance between the edge and our copper, and this is what that does. Now, this number here is purely what the manufacturing does. So this is their number, their unique number for our circuit. It doesn't really mean much for us, but it means something for them. So when we have our design, we're evaluating our design, and we want to contact them, say, well, we designed the circuit board with you. Do you still have the design? They probably will have the design, but we have to quote that number at the bottom. Now, it's not something that we added. It is something that they added. You can also ask them not to add that number, but I did not. I decided it is better to have that number there. Yeah, and we can quite easily see that this is the LEDs. And we have our LED circuit running there, which is exactly what happens there. Now, also these LEDs, one is connected to ground. These are our ICs. And also, let's have a look at the bottom side. No, I don't need to do that. Let's have a look at our bottom side without that. Now, also on the bottom side, we do not have the names. Close. Strict. Right. So our board actually really looks the same. It's supposed to be like, let's get my orientation correct. The problem with the orientation is with the PCB design, now remember we are looking through our board to the bottom layer. So with our manufactured PCB, we cannot do that because we cannot look through the top layer. The top layer is not transparent, but with our PCB, it is transparent in the Eagle software. So our whole design will be flipped around. Just bear that in mind. That's why it looks a little bit different. Well, not different. That's why it looks so different. So right, okay, you're seeing that. So this is the power delivery side with our incoming connector there, going through our regulator, feeding into our ICs along with our resistors and everything we have there. Now we have this hole there, and this hole corresponds to our regulator. If you have a look at T names, T place, this is our regulator. Do I have that regulator? Our regulator looks like this. Just take away this board. It looks like this. So the idea is that the regulator would stick through and then you would bend it flat like that, which we will also kind of do. I don't like doing it because I don't like bending these rigid components. It feels a lot like I'm breaking them, but you just have to be very careful. So, okay, so we have our board. We have our components. My soldering iron is heating up. Now I will be attaching a couple of components. I won't be attaching all of them, just because it will take way too long and I don't think it's that interesting. Now I will be using my soldering iron, so I will be facing away from my computer, so you might not hear me clearly, but you should be able to see me clearly. What I especially like with this is that we can check if all of our components fit. So this especially, I was worried about that my switches would not fit, but they fit amazingly well. I'm actually really surprised that it does fit so well. So they just sit through. So how you add in your components, it's not self-explanatory, but because we have through-hole components, and this is where we designed it, all of my through-hole components I insert from the top layer. It goes through the correct holes, and I connect them like that. Now, the first components that I would like to connect is these IC beds. Remember, I'm using these IC sockets, and I will solder onto these IC sockets and attach them. Now, once again, you might see on the silk screen, we have our IC numbers. It doesn't tell me what IC it is, but therefore you look at your parts list and you can look at what is IC1. Now I know it's exclusive OR gates, and just have a look at that if you want to create your board. So the first thing is, let's solder together, let's say IC2. So I insert my board. It's a dual inline package. I'm inserting it and putting it onto my camera so that I can have a look at I'm showing my screen so you can see what I'm doing. Now these pins are so fine that you really can't actually see them. Even if I try and get the focus just right, you can't really see the pins even on this magnified blade, but you can see them at the they are there and they are sticking through. Let me just see if I can show you from the side. That is the component being stuck through, and these I will now solder on. So I usually stick through my components and then place it on my top side. So the bottom side is sticking up and the component is pinned together. Okay, so now I'm going to be hopefully not making a total mess of this. So I'm using this soldering iron. It's got a relatively wide tip. That is just so that, let me just do this. So I like a wide tip, so a little wider tip better, because it has to make contact with the pad, the shiny bits you can see there, and the component at the same time. It then has to, then you can use it to mount the components. Now, I have to admit that I am not the world's best soldering technician, but I am capable of soldering, but I'm not a professional because it's not really my job, but it's something I can do. Right. So the idea is that we touch our soldering iron to the component for a short amount of time, add in the solder, and create our joint. So once again, the idea is that the soldering iron makes contact with the pad, the PCB, the exposed metal pad, and also with the component as well. You keep that there for about half a second, and then you touch the soldering, wire to that, and then the solder melts and then flows to the warm components and make the connection. Sorry, it looks like a fly has invaded my space. Okay, so I did not share my screen. So you did not see that. Brilliant. Right, so I just finished with this layer on this side. Now let's swap it around because I am right-handed, so it's easier for me to solder pins on the right side. And right, so as we spoke about, the idea is touch it, heat it up, and then just add a little of solder. So, um, so sometimes it does go as well as done there. I'm glad it did, because a lot of the times it does not go as smoothly as that. So once again, I make contact with the pad and also the component, and then after about a split second, then I touch my soldering wire to the component. It melts, runs to the warm components, and then makes the connection. And then I move on from there. Now you'll see that I try and use as little as possible. If you have a very big blob, it is pretty bad. That does not necessarily make a good connection. What we want is that because both components are heated up, the solder runs and attaches to both, making a very good connection. Soldering joints like this, they kind of need to look a little bit of little shiny. If they're too dull, that means it's not a very good connection. Now we'll also see a couple of things. So I've shared my screen. So this is my solder connection I made now. You can see that the solder is just only on the pad. It does not run or is not spread around my board. And we also have this shiny elements here. Now, what is that? That is something we call flux. Now, flux is contained within this metal, and it just helps with the spreading of heat. If I have SMD, sometimes I will attach the flux separately. Now you do just clean that off. You just wipe it off and it doesn't make a difference. Now back to sharing my screen. So we've attached our component. As you can see, all the soldering joints, they look really nice. And I'm quite happy with this, with my soldering work here, which is amazing. Next, let's attach let's attach the 10K resistor network. I'm just going to show you what it looks like. Our resistor network that looks like this. I'll just put it on the screen. And that is what it looks like. So once again, the resistor networks are not directional. They are, and I know this is R1. So once again, I place them through like this from the top side, and the pins stick out on the bottom side. I place it down like so. And you can't really see the pins, but that is fine. Now, the same procedure for these. And that is also done. So you can see these connections they look good. Now these components, let me just turn like this. Now the resistor component, its diameter legs they were a little bit bigger than my IC socket. Now what that makes a difference of is that it takes a little bit longer for the component leg to heat up. So that is why I just spent a small time longer with my soldering iron to make sure that it is properly heated up. The next component that I want to attach is my regulator. Now this is a little bit of a bigger component. Now with my IC and with my resistor network, I did not have to snip or remove any of my pins, because you do have resistors with very long leads that stick very long through my components, through the board. And this is also the case of this IC. Now you will have to cut down those legs. Now there is a couple of problems with that. What I used to do when I was a student is that I would solder my component like that and then cut the legs or the excess legs later on. This is generally, most of the time, it works. But what may happen is that when you solder or attach the component and then use pliers to cut down the component, make the leg shorter, what might happen is that the soldering joint might break. So because you are putting a lot of force in trying to cut that component, especially if it's very thick wire, like this, the component might break, which it does happen. It really does happen. So as far as you can, try and cut the soldered components beforehand. So what I try to do is I try to bend everything into place. So with this, we can bend it down so that it sits like it's supposed to. So I've just bent my component so that it sits like there. So why does this regulator sit flat and why does it have a hole inside there? Well, that is all part of the ground connection. Now, I did not include it as my ground connection, but you can use this like hole to spread the ground connection from your top layer to your bottom layer. That is something that you can do, but I didn't do. I didn't need to do it. You can also attach the regulator there with a screw or something, and just fix it in place. Or you can attach fins to it, a heat spreader. Because these regulators, these power connectors sometimes create a lot of heat. So sometimes you have them freestanding up like that. And then you can attach a fin stack to it, which helps with the cooling. Let me just Google that and make sure that you guys understand what I mean by that. Sorry, I'm just, you're staring at me, Googling something. So these aren't exactly the correct ones, but I'm not going to search for the specific correct ones. I'm sharing my screen. You might have these elements here, and this is to help with cooling. So you might have this attached to your IC, and that then helps with the cooling or dissipate heat. But I don't really need it. This is not a very high power IC, so I have my IC bent with the legs sticking through. Now what I can do is I can bend the legs a little bit more. I usually try and bend them. What that does is the IC then sits then finely. What I can do is then I can cut one leg. So I cut just one leg and have the other leg still there. Cut it to a size that I want. So now you won't see it. Well, let's see if I can show you on my little screen. I'm sharing it. Now you can see that these legs are still long and this one is cut down. Now I can attach that one with solder, which I'm going to do right now. Just orientate it so I can have a good, and so I'm going to be attaching this one leg. Get a good look at it. So we have the one leg attached. Now, because we have that attached, that means our component is now, it's roughly there. It's roughly it won't move around. So now I can cut off the other legs as well to a size which I like. And then I can solder them on as well. So I've shared my screen. Just get to the power attachment circuit. Get my soldering wire. Just have a look at. Right. So now I have attached just a couple of components, and I'm just sharing my screen once again. And this is what it looks like on the top side. So here I have my IC, well, my power converter, which I bent over. This is one of my IC sockets. And then this is my first resistor network. Now, as you can see, let's have it like this. So this is IC1. It does not tell me that it's the exclusive OR circuit, but I know that it is. So I then have my, I go and have a look at my netlist. Where is my netlist? Well, let's click on this. I probably did not have a look at it. Let's export and have a bill of material. Here I can have IC1 is my 74LS86N, which is my quad input exclusive OR gate. So I will have a look at my the components. I have IC1. Okay, cool. What is IC1? It is my quad input OR gate, and then I will attach that there. Right. So once again, I cut down my components before I solder them. The idea is that if you have pliers like this, you're actually applying a lot of force. If your pliers aren't sharp, or not sharp enough, if they're not good pliers, you'll struggle and then you'll apply a lot of force, and that can break the solder joint. So I would recommend soldering the components, well, after you've cut them down. So first cut them down, you sort of like bend them so that they sit in so they sit in a way that it won't move around. Then you solder them, and then you check your connections. Right, now I won't be soldering anymore because it does take a lot of time. I will be soldering it in my own time and then just showing you the result. And yeah, that's pretty much it. So soldering, once again, I like to have what we call a chisel tip. Let me just see if I can have a. I'm looking for an example of what the specific tips look like. But I'm not finding ones so far. Yeah, that's not fun. Right, I'm just sharing my screen once again. I just Googled a couple of tips. So here on the right side are a couple of soldering tips that you can choose from. Now, a lot of people think that you need something that is really sharp, like this one on the right or this one here. But that is not necessarily the case. What you have to remember is that you're dealing with heat transfer. So if you have something that's very, very pointy, you're only really transferring heat where it touches the component, which is at that point. So it does not transfer a lot of heat. It transfers a lot of heat just to that small point, but it doesn't have it doesn't work. Ideally, your tip should be as wide as your pad that you're using. So you can just put the tip down on the pad at some angle. It's 45-degree angle is probably better, but it depends on you. So that it makes contact with the whole of the pad, heating up the whole pad, and also pressing against the whole of the one side of the component. Then it transfers a lot of heat and a lot of heat efficiently. So what I tend to go for or use more often than not, depending on my pad size, is one of these bigger chisel tips. So it's just a flat chisel tip so it can sit nicely against the pad and also transfer heat really quickly. Don't always go for these, the sharp needle points. You'll struggle because they do not transfer heat really nicely. Like I said, I like the chisel tips, and they make your life a lot easier. Try and use tips that are roughly as big as your pads or as big as tip as you can get away with. And experiment which ones work for you. Because I've found the tip that I really like, and I use that pretty much always. The needlepoint tip I only really use for very, very, very small components, um, like some surface mount components, or if I have a very tricky, so like IC with very, very tricky components. But otherwise, I just stick to one little tip that works for me. Okay, let's take a quick break, a quick 5-minute break, have a drink of water, and then we'll continue on with looking at our board and then EagleCAD. See you guys in 5 minutes. So, right. So this is pretty much all, well, I'm going to do now about this little board, because I will solder on everything else and then test it. And then if it's successful, I'll show you, or if it's not, I'll show you why it wasn't successful. But this is just a small, like, side bit about soldering, because this class is not really about soldering, but you need to understand when you are designing these boards, what they look like, how the final product looks. Because most of the time, you need to create your boards also with assembly in mind. That means that you will have to understand how big your components are, where they fit on your board, and how easy it would be to assemble these boards. Because mine is relatively easy to assemble, because there's lots of space in between components, and I can get my soldering iron in there. But whenever you do design your boards, spend a little bit of more time looking at like the 3D generation of the board, just to make sure that everything is fine and that it can be assembled as well. Because you remember, you have to stick through the components, add them, and if you have too many components too close together, it makes it really hard to assemble your board. But yes, so I'm actually quite happy at how this turned out. Also, if this is something you're interested in, practice soldering. You don't need to practice it that much. Just try attaching your boards as well. The good thing about soldering is that if you make a mistake, you just desolder it. You heat up the joint again, use tools to remove the solder, remove the component, and then just do it again. That is another reason why I'm using these IC sockets, because they do, some ICs are really sensitive to heat. So if you're struggling with soldering, you might have the soldering iron on the component for a little bit too long. Because remember, the component, it's metal, and that metal conducts heat really well, and that then conducts heat inside of the component, and it may destroy the component, because these components do have heat tolerances, a tolerance to heat, and or some tolerance to heat, and then that might damage it. So I tend to use, especially if I have components which are sensitive, I tend to use IC sockets, and then you can just insert the components later on, and that is fine. But for a lot of components, that is not an option. SMDs do not have IC sockets, so you just have to be very, very careful. And just remember, when you are soldering, or when somebody is soldering, the soldering iron is a couple of 100 degrees Celsius, so it's really, really warm. And when you have finished soldering component, it cools down quickly, but it is still warm, and you can still burn your fingers quite horribly with these components. Just be careful if you are doing soldering, so that you don't burn yourself, because it is really, really hot. Also, when you are soldering, try and do it in a ventilated area, because the soldering, as you might see, when the soldering does melt, there is a little bit of smoke, a little bit of fumes, because you are melting metal with flux in, and some of those fumes you might inhale, and they are not the healthiest thing. They're not poisonous, but just be sure that you're soldering in a well-ventilated area, so those fumes are carried away. Right, that's all being said. Let's now continue on with looking at Eagle. So what we're going to be doing now is we're going to be creating custom components. It's quite common to not find the correct component that you're looking for. As we spoke about Eagle, its search for components is really not great. If you just misspell the name of the component, it will not find it. I think they are fixing the search function in the next version of Eagle. or for the Fusion 360 type follow-on, but it hasn't been fixed yet. So you will have to be very good at finding a certain component or finding components to be able to find those components. Otherwise, what I tended to do quite a lot of times is just make my own components. And that is what we're going to be doing now. I just have to open up a couple of things which I forgot about. Layout. So we're going to be completing, excuse me, we're going to be creating a couple of components, custom codes. We create the symbols, create the footprint, and then use them in our designs and see what they look like. But a lot of these components are like the dual inline package 14. That remains the same. So I can also substitute a certain component for my component. Let's say I'm buying an IC. I can't find that specific IC in Eagle, but I do know that it is a DIP 14 package. Then I can use another IC, which is not the same, but if it has the same DIP 14 package, I can use that. So you can substitute certain ICs or certain elements for other elements if you know that they have the same shape. For instance, for these, my network of resistors, I know it uses a single inline package. So I could have found the resistor network, or I just could have used a single inline package with that amount of pins. If I have 8 pins, just use 8 pins. But it is something with more practice you'll get more better in. But I'm just hoping to equip you so you can make your own elements. So let's have a look. I'm sharing my screen. Let's start with a SMD variant because they are generally sometimes the hardest. This is a data sheet of SMD components. So you'll Google, this is SMD components. I just Googled and found this online. Here is the code. So this SMDs, if I have 0201, these are its specific dimensions. And you can see it's height, width, length. And what I'm more interested in is the solder pad land pattern. So this is what it looks like or will look like where the solder pads are on your board. So let's start with select the biggest one just to make it a little bit easier. The 2512, so we'll create this component, the 2512, and we'll create this component, and then we'll see what it looks like. Right, so this is Eagle, so we'll go to File, we'll create New, and then we go to Library. So we've done schematic, we've done board. Let's create library. So click on library, and this opens up. Now I would recommend that you save as. So it'll want to save your library as something. So let's have it as our class of 2023. We save a library, and here we have all of our other libraries, and we click save. So now we can see up top, here it changed libraries, and we are dealing with our class 2023 library. Now here we have a couple of columns. We have a device, footprint, 3D package, and symbol. And they represent exactly what you would expect them to represent. We have the symbol schematic of our component. We have a 3D package. If you do have a 3D model, we've got the footprint, and then we have the component name. So we'll start on this side, on the right side, on this symbol area. So we click add symbol. What is the symbol name? It's a resistor, and it's specifically the 2512 resistor. And we click OK. It'll ask us, do you want to create this component? Yes. And this is a familiar sort of like looking screen where we have our component selections. So here we have our grid. We can change a grid to what we want. So like I keep on saying, I like to use millimeters. And I would like my grid on. Now, I do always, not always, I do tend to use millimeters a lot more than anything else. But make your life easier. If the design that you are looking at, the physical dimensions, are in inches, do not waste the time converting inches to millimeters. Just use inches. If the design lengths are in mils or whatever, just use that dimension. My specific one that I'm looking at, it does have inches and millimeters. I prefer millimeters, so I'm going to be using millimeters. But if there was only inches, then I would just use inches. So I've shared my screen once again. Here we're dealing with the 2512. So first we're going to be looking at the solder pad land pattern. So A is the pad length, B is the pad width, and there we have a gap in between. So let's look at pad A. It is 3.5 millimeters long and 1.6 millimeters wide. So we'll use these two to create our pads. So these are all the same which we know. We have information, show, group, move, mirror, rotate, copy and paste, and all this stuff. The new one is now this one. I click on it and it is pad. So we can have all of our pad types which we want, but we'll get through all of that in a second. But we can place down our pad. And now remember this, the symbolic does not care if it's the symbolic does not care if it's surface mount or through hole. It just cares about the symbols. We're just creating the schematic, and then we'll continue on with the footprint creation. So let's create our one pin and our other pin for our resistor, because we need 2 pins for our resistor. We can click on info, click on pin, and it gives us our little bit of information. So let's have our pin. We call the pin number 1. Here we can adjust our X and Y position, at what angle it is, if you want to have it angled. And we have a new option called direction. Now direction, we have NC. Now NC stands for not connected. So if you have a pin that does not do anything, then you have not connected. We have, if it's only, if the signal only goes in, we use in. If it's only using out, out, or IO means in and out. We have OC, power, passive, high, and supplementary. So most of the time, if I do not know exactly what the pin does, it's in, out. And we can have short, a short length, we can have a middle length, or a long length. So let's have that. And function, is it a clock? Does it do a dot function or dot clock? We don't care. And do we want the pad and the pin both visible? Let's have the pad visible, the pin visible, and both visible. Let's just have both visible because that's what I like. And so resistors are quite commonly input outputs because you can connect them both ways. But if you do have a component that's directional, you will have inputs and outputs. Or if you have an IC and the IC only has got inputs on the one side and outputs on the other side, you make all of those inputs. It does not make that much of a difference. Where it does make a difference is that when it does the electronic rule checking, it can tell you if you have accidentally attached a signal that it sees as an output to an input pin or something like that, then it'll just tell you if it is. So add in as much information as you can. So I'm sharing my screen once again. And then we can start drawing. So let's draw a line. Now, once again, we can have something like this if it's our custom resistor. We can have, obviously, our 90-degree bends if I want to create a resistor like this. It does not really make that much of a difference. Let's say I want to have a resistor. Let's just do this. I am having a unique resistor that looks like this. Now, once again, this is up to you how you create your resistor, but just make sure, because this is going to be showing up in the schematic, and then the schematic will then somebody else will look at. So you will have to create your symbols and it should look like something familiar. Now, let's say this is a totally new resistor. It performs a different function. So I would have something like this. But if you have a standard IC, just use a schematic symbol like a standard IC symbol. So once you are happy with the pattern that you have created, I now have to add in a text. Now all ICs have names and they have values. Now we have to do the same thing as well. So I add in the names. Now it has to be this greater as synchronal, and then names all in caps. Oops, that is wrong. I do not want to do that. And I click OK, and I place it on the names layer. I place it where I want it to be. And then I redo this, and I have value, sorry. And I place it on the values layer. So now I have my component. It's got two inputs connected to it. It's got names and it's got values. Now what I can also do is move around these elements. Let's just leave it as it is. This is fine. I can save my component. And now we've created our schematic value of our component. Now, if we now, let me share my screen again. If we now close this, we open up our library again, class 2023. We can see that our element is now there. We click on that, and that is our resistor 2512. Now what we need to do is we also have to add in the footprint. So let's also add in the footprint. We also call the resistor 2512. And we create a footprint, and we have this element here. So once again, I'm going with my millimeter grid. just because my design is in millimeters. And I look at my pins again. It is 3.5 by 1.6 in width. And now our standard elements. Now, what is new are these two elements here. These are through hole and SMD. So let's start with the SMD. We click on SMD and it creates a pad for us. Now, let's just place down the pad. It will place it in the middle of that component. And if we click on our information, it gives us some information. Now we can change this to pad number 1, and we can change the SMD size. So we know that it is 3.5 times 1.6. And we don't really care if the roundness of it, it's fine. We have our one pad, sorry. And then we add in another pad and make sure that it is also, oh, no, the correct size. 3.5 times 1.6. And I need to change my name to pad number 2. Now these two pads are now the correct size. So what do we need to do now? We have to make sure the third is the C element here. So here, C, the distance between these two are C 3.8. Now you'll have to be very, very careful because that is now you're dealing with distances and it's really hard to figure out which distances are what. So what I suggest is just write down a couple of things. So write down drawing schematic because you now have the pads. I know my pads is the width is 1.6 millimeters. So the distance between the side to the middle of the pad is 0.8 millimeters. So now we will have to, we work from the middle, the midpoint, because that's where our grid starts. And then we can move back. So we have 0.8. And then how much distance is left? The gap is 3.8 between the pads between the middle and the pad is then 1.4. So then that 1.4 millimeters plus 0.8 is 2.3 millimeters. So now I have this. I can click on my information. In my position, I have minus 2.4 millimeters. This position, I also have 2.4 millimeters. So this is my X and Y coordinates. Click on OK. Now I can text my dimension. Between the middle, and then I can check if it is correct. I can make my grid a little bit smaller. 0.1 millimeters and make my alternated a little bit smaller. And then I can see the distance is 1.6. Minus 1.6, 1.6. So that is 3.2 in total. Am I making a mistake? Yes, it is, because it needs to be 3.8. So we have to include 2 more millimeters, 3 more millimeters. So let's change this. So a lot of the times you will have to play around and figure out which ones work. But let's see, 1.6, 3.2, so I'm missing 8, 3.4. See, sometimes my brain just doesn't work. Once again, it didn't work. So the problem is that I'm not writing down I'm not calculating, I'm just sort of what we call eyeballing it, which is not great. So 1.8 plus 1.8 is 3.6, which is 3.8. So we need to increase it one more. Keep on making my silly mistakes. So now I can see what I'm checking now is, I have to share my screen because you're looking at my face. Shouldn't look at my screen. Now I can see that my 1.9 to minus 1.9 to plus 1.9, I'm looking here at the grid up top there. So now the distance between these are 3.8. Let's have a look at that. Now 3.9, I'm just missing it a little bit. Yeah, it's fine. This is, no, it's not working. Okay, so now I've placed my pads down correctly. I just save it. Now the next thing that I can do is to create the physical component itself. So I will need to create it's got a length and a width of 6.3 and 3.2. So let's create a line. Usually I start at the origin. Now I'm working on the T place elements. So once again, T now stands for top place, bottom place, top names, bottom names. If you have got a component with these elements in it, just make sure you're working on the correct layer. Now we're dealing with surface mount components, so we're working on the top layer. Let's add in a T place. So it is, I just want to bring this up again and move this to my screen here. 6.3 millimeters. I start at the origin. Draw a line 6.3. I move that line. So I know this is now a 6.3 line. I can copy this line. And now my width line is 3.2. So I have this. And I can might as well have it minus 3.2. So what I'm doing is I'm using like an old, oh, now I've connected these lines. That's not what I wanted. Let's just move this out the way. So hit that. And I also copy this line. So what I'm doing is I am using a CAD trick. So when you're doing drawing, and if you don't have good tools to draw an exact line, you start from the 0-point line and move down and have a look at the grid that you're using there. So I want to have a line that's exactly 2.4 millimeters. I move my cursor until up here it adds to 2.4, and then I draw that line there, and it's 2.4. Now I can move my elements in here, so I can have a look. It's roughly there. This will be so I now have my component like this. And now the next thing I need to do is have an element called T keep out. So what I'm doing now is every single component has got an area around it where other components can't move into. And this makes sense because your component is a certain physical size. So that physical size cannot be in the same place as other components with also size and mass. So I create a border where everything inside of it, no other component can move into that space. We'll see how that works once we use the design a little bit. It is called the T keep out. And I draw a line or an area around my component. And this is the T keep out zone. So once again, T keep out zone, that means just no other component can be within this zone. The next element we need to do is, of course, we need to add in our names. So we add in, once again, names. And we have it on our top names layer. And then also if we have values, we have our top name values. And we're applying it. So what does the names and values do? Well, those are placeholders for the user to import their own values and names. So if I have a specific name for this IC, like if I want to call it IC number 1, IC 2, 3, 4, 5, whatever, then that space then occupies our names. And if it has got a value like 800 ohms, for instance, now it will be, it'll come into those values. It'll add in, or it'll slide into those values. So the names and values are important because if our user changes the names in the schematic, those we have to have a sort of like a container that those names can stay in. And then also in the footprint needs to have the same names as well. Okay, so I have now created these elements. Let's save them. And then let's open up my library. 203. And now I've got my symbol. It looks like this, and also my footprint. Now the next step I need to do is I click on Add Device, SMD. I give it a name that makes sense. 2512. And I click OK. And it asks me, do you want to create this new component? Yes. Now we end up in this area here. Now, the first thing we need to do is we add a part. It looks in our library for all of our schematics. So we only have one schematic, so that's the only one we can choose. We click OK, and then we place it down. I would recommend placing it down somewhere in the origin, because this is the place now where we will be manipulating our component. I click on New and Local Package. What does that mean? It means that I've created a couple of packages on my PC and I want to create it here. You can also add one from the web, but we have created it, so we click on Local Package. It also looks in our library now for our number of packages. This is a packages we have, which we just created. We click OK. And now the next step is we have to connect it up. Now, clicking on Connect, now we have to map our symbol schematic pins to our footprint pins. Now, both of them have 2, which is great. So we just click on, so pin number 1 in our footprint connects to pin number 1. That is fine. And 1, 2 goes to number 2, which is also fine. And then I click Connect. And now I can save. So what then happens? Look at my library. I've now created a component from my footprint and my resistor. Okay, and that's pretty much as far as our class can go today. So we're running out of time. So in the next class, we'll quickly look at creating a through-hole resistor and then a couple of pin arrays. And then we'll use them in a design, which is exciting. And also, hopefully, by the next class, I should have my board all assembled. Hopefully, we'll see. And then we can test it in class. Right. I hope this was slightly exciting. I like this. I like soldering and creating boards and creating circuits. And I realize it might not be that exciting to watch somebody do that, but it is an important thing that you need to see somebody do. And, because that's the end part, or the what we aim to do with this course. We want to be able to create PCBs, select the correct components, create our schematic and our PCB files, have it made, and then construct our circuit all by ourselves. Right, so I'm ending this class right here. Hope you enjoyed it. I will see you all on Wednesday. We will continue on creating custom components and then using them in our PCB circuits. Right, have a wonderful rest of your Monday, and then I will see you all on Wednesday. Bye-bye.